So this is the today's topic and microprogramming. This is the fourth unit. There's a very simple concepts that are there in this particular one. Okay, so the huge concepts I've discussed already in the previous class. Okay, let us recapitulate what we have seen in the previous class, and then we'll go for the SM charts. Okay, recap. By the way, have you tried to write the program, or shall I write the program for the last class? So the last class we have started off sequence detector. So what is the method that we have used there? A sequence detector is something like this. Having input is called X. It will produce an output Y, provided there is a clock signal and there is an RST signal. So we did not mention explicitly RST signal, but the RST signal also will be there. Okay. So for this one, the state diagram that we have given, the state diagram is S0. We have an S1. We have an S2. Visibility purpose, I'm using red color. 0 here, output is 0. Otherwise, it will go to the side. If it is 1. If it is 1 here, it remains in the same state. But if it is 0, it will go to the next state. If it is 0, it will go to the next state is initial state, 0 by 0. And it will go to this particular state if it is 1 is there. But output is 1. So this is what we have to find. So therefore, by looking at, instead of taking the truth table to understand the sequence detector, better to identify this one with the help of state diagram. Okay, this is called state diagram, or we can call it as state graph. Okay, so one and the same. Okay, now okay, so if you want to design your circuit, so once we have a information in the form of a state graph, so if you want to design this one, we have to know what is the subcomponents that are involved in this one, right? Okay. So by the way, how do we generate the truth table from this one? Actually, the truth table, we feel that is a comfortable way to understand the behavior. Okay, but the state diagram we are giving, how do we generate the truth table from this one? Okay, so from this one, the truth table is something like this. We have a present state here. Okay, so better we have to write the next state and output Y. Okay, if you are there in the S0 position, okay, depending upon X value, depending upon X, whether X is equal to 0 or X is equal to 1. Okay, so therefore from the state diagram, you can easily identify this one. So if you are there in the S0 position here, okay, if you're there in the S0 position, where you have to move, if it is 0, you should be there in the same state, right? S0 state lone undali. If it is 1, we have to go to S1 state. So this is S1 state. What is the output? Output is 0. Similarly, if you are there in the S1 state, if X is equal to 0, ఈ స్టేట్లో ఉన్నప్పుడు మీరు X 0 అయితే ఎక్కడికి వెళ్తున్నారు? We'll go to S2 state. S2 state. If it is 1, remains in the same state. Here also the output is 0. Now, for example, if you consider S2, 0 అయితే ఎక్కడికి వెళ్తున్నారు మీరు? Where you are going to 0? 0 means you are going for S0. S1 means S1 అంటే ఎక్కడికి 1 అయితే ఎక్కడికి వెళ్తుంది? S1కి వెళ్తున్నారు. So the output is 1. Okay, so again, this is what actually the concept. Just a second. Okay, so here in this way that we can write. Okay, this is what the truth table is all about. Sorry, I have to write this one. So this is what the truth table is all about. Okay. Right. So please remember this truth table while we are writing the program. Okay. Okay. This is actually a compact form, or this is also called as, instead of calling as a state table, we normally call it as, it is a state table. Okay, so we have not mentioned any kind of state assignment for S0, S1, S2. Okay, so how many bits are there for this one? State assignment. How do we do the state assignment? The state assignment is for S0. How many bits are required? 2 bits. 0, 0, 2 bits. For S1, 2 bits. That is 0, 1, for example. For S2, 2 bits, 1, 0. Okay, so S3 is not there. That's the reason why I'm not using the 1, 1. So therefore, by giving the values here in this way, it is also possible to develop the extended form of the truth table. Okay. So therefore, what is the extended form of the truth table now? So these are very important when you are designing circuits, this point of view. So extended form of truth table. Okay, if you want to develop the extended form of the truth table, so first we should know what is the content available in the this particular main block. Okay, so something like this. Since it is a sequential circuit, everybody knows that. Okay, a sequential circuit consisting of a combinational block, okay, and it is also has got memory. So it is identified, it is affected, or this is changes its value by primary input signal, and it will produce primary output signal, right? Primary output. So the part of the output we are treating as the next state and connected to it as a present state. Okay. Now this is what actually available inside of your main black box. So this is what we have seen in the last class. Don't forget about to write the clock signal for the clock. Don't forget about to write RST signal. So here, instead of writing the primary input, normally we are calling as an X. Instead of the primary output, we are writing as an output is Y. Remaining thing I will say primary present in present state, next state will be the internal to the circuit, right? Okay. So here, um, so this is the basic diagram that is required. It is required to write a program, to write a Verilog program. So this is the first thing that we should notice. The second one is we should notice this one. Okay, that these 2 points are necessary to identify to write the program. Okay, there's so many methods are there to write the program for this particular architecture, but we use completely behavioral modeling for this one. Okay, so only 2 or 3 steps I will write, and accordingly that you are able to write the program. Okay, so for example, let us write a module here. Sequence detector by using behavioral modeling, or I can say the sequence detector of 10101, for example. So it requires X, clock, reset, Y. See, Whatever the way that I'm writing here based on the state diagram, the same thing is applicable in the the current chapter. Okay, so these basics you should know very well. Then only I'm not able to write the programs for the chapter number 4 problems, because these are fundamentals. You can understand this one carefully and apply for that examples. Okay, that's the reason why I'm spending time on this one. Okay, next inputs are x comma clock comma reset, and output is y, right? See, carefully understand. I'm going to write one always statement for this one, another always statement for this one. Okay, if I know the internal structure of the memory, if I know the internal structure of the combinational circuit, then I will go for behavioral data flow modeling, or maybe a structural modeling. I can write it. Okay, I don't know anything internal structure of the memory element. I don't know the internal structure of the combinational circuit. Therefore, better to write it in the form of a behavioral modeling, because we know the behavior of the memory, we know the behavior of the combinational circuit. Okay, so it is very important to note that number one, behavior of the memory behavior is based on input output. Okay, so therefore from the input output that we can write, for example, next state is the input, present state is the output. For this one, just only the input output behavior only we need to write. Whereas for the combinational block, combinational behavior, this is also done with the help of input output behavior only, but which is based on, here in this case, which is based on state diagram or state graph. So therefore the state graph will give the information related to the combinational circuit. Okay, depending upon the present state as well as the present input condition, it will produce the present output and the present next state. Therefore you can see carefully, the state diagram is always saying that, so okay, the present state of the system and the input condition and output condition, what is the next state, that information is only available. Okay, so that is very resemblance for the combinational block, right? Memory is for only just input output behavior only. Okay, so therefore, so for this one I'm going to use one always block. Here I'm going to use one always block. So here also I'm going to use another always block. Okay, so let us write here always at the rate of posage of the clock and posage of reset signal. What has to happen if reset is true? ఏం జరగాలి? Let us consider present state is PS. Don't write it is PS means P dot S. Don't write like this. Okay, so dot is not allowed. Okay, directly you can write PS here. Present state is equal to 2 bit of 0 0. Okay, so because we are writing the 2 bits only, we are writing. Okay, next else, it is not true. Else, if reset is not there, depending upon the clock signal, what has to happen is simply a deep flip-flop method. Okay, next state will be treated as a present state. So only the memory purpose is here is to store the information. That's all. You don't do anything with that. Okay, therefore the present state is assigned by sorry, present state is assigned by next state. Okay, okay. So you may ask the question, sir, where is this present and PS and NS are available? Okay, therefore it is internal to the circuit, right? So it's better to write as a register data type because it is in the always block. Okay, register 1 down to 0 of PS comma NS. Intana present state and next state. Fine. We take another always block for combinational circuit as well. Okay, so we write always at the rate of, what is the factors that is influencing? Okay, the combinational circuit, the output is actually Y, another output is next state. These two are influenced by present input, the present state of the system as present input of the system. Right, this information where you find, so that means those two are can be called as, sensitivity list. Am I right? These two are considered as a sensitivity list. Now this, how do we write the program that is based on either state diagram or maybe this one you can write it. Okay, so better I'm going to use this state table because it's very easy to write. It's very easy to identify the operation. So carefully understand this point. Okay, see here. So I'm going to write in this way. So because I am going to consider this the one case statement I'm going to use. Okay, so this is the one case, this is the second case, this is the third case. Okay, so how many bits are there for this one? 2 bits. For this one, 0 1. For this one, 1 0. Similarly, wherever you find S0 0 0, we have to use. Wherever S1 0, something like this we can write. Okay, so let us write here. So let us begin. Okay, see here. So I'm using the case statement. Okay, case. So the case is depending upon the present state, right? So the case is depending upon the present state. So I have created the present state previously. That present state I'm taking into consideration in this one. Okay, so that means that whenever the positive edge of the clock is active, then the present state is generated, and depending upon the X input, it will be taking into consideration the combinational circuit, and it will produce the output as well as the next state, right? So therefore, that's what I'm writing here. So the case is equal to, for example, 2 bit of 0 0. Case is equal to bit of 0 0. It means S0 state low, not apply. Then what is the output? Now you can see what is the output. So you can see the output we cannot directly say. That means next state we have to mention, output also we have to mention. So therefore next state we have to say, we have to mention. So it's depending upon if X value, right? X we need to mention, right? If X is true, okay? If X is true, what has to happen? If X true, then jaragali. If X is true means this one, S1 has to move, S1 must be the output. So now I'll write next state is equal to 2 bit of S1 stands for 0 1 0. Okay. Similarly, what is the output under this condition? 0 only. Okay, Y is also 0, 1 bit of 0, right? So these are the two statements that we have to remember carefully. So since actually we are writing, two statements after the if statement, okay, it is better to write the begin and end. Don't forget to write that one. Okay, so we have to use begin and end here. So we write begin and here. Clear? So if X is equal to 1, next state must be S1, output is 0. Else, for example, else, so that means S is equal to 1, sorry, X is equal to 0. In that case also we find two cases, right? So these are two cases are available. So you consider that one and paste it here. Okay. So, but the thing is that what is the S0 next state? Next state should be S0 0 0, same position it will be. So this is what we are talking about. This is what we are talking about. What about Y not? Y is also 0, right? So therefore this is what we can identify for the first step. If the present state is equal to this one, depending upon the X and Y. So we are not bothering about the internal circuitry. We are talking about only the input output behavior with the help of state diagram or with the help of state table. Okay. Shall I repeat the same thing for the remaining cases? Copy and then paste here. And another time that I have to do, because 3 states are there, right? So what is the modification that I have to do? So 0, 1 that I'm talking about. For 0, 1, what I have to do? So better I need to take very. Okay. Okay. So for 0, 1, what I have to do? S1 కెళ్ళాలి. That means అదే state లో ఉండాలి అంతేనా? The same state it should be. Um, yeah, same state. Output is also 0. Otherwise it has to go to S2. S2 కెళ్ళాలంటే ఎంత అవుతుంది? It is 1, 0, right? 1, 0. Okay, output is again 0. So the last case is 1, 0. This 1, 0, x is equal to same state should be 0, 1 only. Okay, output is 0. No, output is 1, it should be, right? Output is 1. Otherwise you have to go to 0 and output is 0. Output is 0. Okay, actually the output we are not mentioning properly. Output we have to mention in a different way. That here also we should mention it is usual notation is something like this. Instead of taking the output this way, please remember, instead of taking the output in this way, so we have to mention the output this method. So by 0, by 0, by 0, by 0, by 0, by 1. So this is actually the notation, output comma output. So this is the usual notation people will use. Next state followed by output, right? So in that sense, it is a very meaningful way. Okay. Finally, we need to write the default. 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 What is the next state? Let us write begin. And next state is equal to same state lo unmani cheptanu. Next state is equal to initial state 0, 0, and output y is equal to also 1 bit of 0. So that's the best way. Okay. Finally, we need to write end case. So we have to write the end. Finally, to write end module, right? So this is what we can write the Verilog program. I hope you can understand this problem, right? Understood? Is it clear to all of you? How I have written?
Yes.
If you find that any sequential circuit, okay, this is the only the method you have to follow. Okay, so different ways are there. Actually, for example, if you want to write in a structural modeling, we should know for the sake of explanation, for the sake of simplicity, I'm writing here. For example, if you want to write here combination circuit, you're writing structural modeling, you want to write structural modeling, for example. Okay, the structural modeling combinational circuit is required and memory is required. So actually the memory is actually a D flip-flops, right? So 2 D flip-flops we have to consider. Okay, so therefore the output of this flip-flop is actually coming from Q1 plus, the output is coming from Q0 plus, so it is actually Q0. This is called Q1. So this information is gone. Okay, they must have said, okay, so this is actually given by the data flow model equations we can write. So we can generate the equations based on X, based on the Q0, based on the Q1, and it will produce Y as well as the Q0 plus as well as Q1 plus. So like this, by using this particular architecture, we can do it, the structural modeling. but it's very consuming tasks. Therefore, it's better to use in this method only, right? Okay, if you have a more detailed discussion of the structural molding, you please send a mail, meet me, or meet me personally. I will tell you how to do this thing. Okay, so because of lack of time, I'm not able to do the structural modeling for that. Okay, so thank you very much. Now we'll go for another session. The original, uh, the unit number 4 that we were going to talk about. The next concept is SM charts. So let us talk about some theory behind this one. Okay, first and foremost important thing is that it is an alternative way to the state graph. Okay, whatever the state diagram that we have seen, as the complexity of the state graph is increases, as the more number of inputs and more complex things are involved in this one, state graph or state diagram method is a very tedious job. Okay, so therefore we have to use another method is called SM chart method, state machine chart. So SM stands for state machine, state machine chart. Okay, so SM stands for, S stands for state, M stands for machine. Okay, this is a chart. Okay, this is alternative to the state graph. Please remember that point. Clear? It is also called algorithmic state machine, also called as algorithmic state machine. This is nothing but ASM. This is also called ASM, algorithmic state machine. Okay. So preferably these SM charts are most preferably used for the control control unit generation. Okay, for generation of or for design amateur, as simple as that. For design of control units, we use state chart, state machine charts. So normally any digital system is converted into converted into a data path unit and control unit. Okay, so therefore data path unit will perform the operations. At what time what functions must be operated, that is decided by the control unit. Okay, that is what the broadly classified the any digital system. Okay, for the sake of simplicity, I'm telling you that any digital system will be divided into two parts. Okay, one is a control part, control unit it has got, as well as it is a data path unit. So therefore, so the sequence of operation, at what time what operation has to perform, that is decided by the control unit. Data path have got a real hardware, it will perform the operations. Okay, so therefore for the control unit purpose, we normally use state machine chart, not necessarily, but preferably people will use that one. Okay, preferably we use that one. Okay, now how do we construct this one? Okay, so what is the basic? What are the conditions to draw the state diagram? So far, I have drawn the state diagrams unconditionally. Suppose we know that that's how we have done it. But what things are taken into consideration when you draw the state graphs? Okay, the conditions must follow. Must follow in order to draw state graph or state diagram. Actually, these conditions are automatically met when you're using the state machine charts. Okay, so later we will talk about this one. What are the conditions? Let us, I'm going to write here. The first condition is that, so one one and exactly one transition from a state must be true at any time. Okay, so something like this I can write. One and exactly one transition, one transition from a state must be true at any time. Okay, so actually this is what knowingly or unknowingly we have drawn, but I don't want to explain more about this one. The next state must be uniquely defined for every input combination, for every input combination. Okay, so these are the two conditions the state graph has to follow. Then only we can depict the meaningful state diagram for your application or for your operation, right? So, but these conditions are automatically met if you are using the state diagram. So no need to. That means we have to, whenever we are drawing a state diagram, we have to keep in our mind accordingly. We have to draw the state diagram. For example, I'm writing here. For example, you consider here, if you're talking about the S naught state, for example, right? So this S naught state will always take the input is equal to zero state only. It cannot take one. Okay, so if you see only zero, then only it will come. Only zero, then only it will come. It cannot come logic one here for this one. Okay, so only one transition it has to consider means this is what. Okay, if one state is taking one particular logic value at any point of time, that logic value only it has to take. No other value you should not take. Similarly, you consider here also. For example, at this point S1, S1 will take logic 1, and similarly S1 is also taking logic 1. It's not taking the logic 0. So here also it is taking logic 1. So all our logic 1 also taken by the S1, not other logic value. So that is what we have to keep in your mind when you are drawing the state diagrams. So this is how we know that whether you are writing the state diagram correctly or not. Okay, so that's we have to follow, and the next state also must take all the input combinations. Okay, so that's what is meaning of this one. So when we are drawing the state diagrams, we have to consider about this one. But when you are drawing this one, when we are drawing the state charts, SM charts, we need not follow this one. Automatically these things will be fulfilled. Okay, so these conditions are automatically fulfilled by the SM chart. Okay, please remember I'm using the words two, they're two different words. So state diagram or state graph, I'm using the SM chart, something like this, or ASM chart. Both are one and the same. Okay. Okay, fine. Next one is, what are the components whenever you are drawing the state diagram? There's a, so far you have seen is a round circles that we have used here. State diagram consisting of round circles, right? Round circles we have used. But what are the different components that we use in order to construct a state SM chart? So the basic components are principal principal components to construct SM charts. So to construct SM charts, okay. So there are the three important components are there. One component is called state box. The second one is called decision box. Third one is called conditional output box. Conditional output box. Okay. So these are look like this. I want to show you. Um, where it is there here. Copy, paste it here. Okay, something like this. Okay, there's three important blocks are there. One block is called state box, as I mentioned in the previously. This is a state box, decision box, conditional output box. What is the responsibility of the state box? It holds the state name as well as the output list. Okay, state name, for example, S0, S1, S2, something like this. Okay, and output list also can be possible to do this one. Next, conditional box says that where to go to the next level. If the condition is true, where it has to go. Where the condition is false, where it has to go. And conditional output list means so when the condition is true, then this particular output has to produce. If the condition is false, there may be a possibility of output produced if the condition is also false. So therefore, depending upon the condition, we have defined the output. That is called, it is a conditional output, right? So these are the basic components we have to use to construct any SM chart. Okay, so for the time later, we are going to construct a SM chart for a particular digital application with the help of these things. So we will see later on. Okay, so for the time being, the basics that we will clear. Next, the next concept is SM block. Okay, SM block. So what do you mean by the SM block? It has one. So if any SM chart consisting of only one box, one state box, then that is called SM block. Okay, it can have a number of decision boxes, a number of conditional output boxes associated with that state. Okay, but we should say that only one state box should have. Okay, so if any SM chart consists of only one state box, only one state box. Okay, it's a very important one. So only one state box, but it may have more decision boxes and outputs, conditional outputs related to, it's very important, related to that state box, that state box. Okay, so that point we should not forget. Okay, so how it look like? So let us say something like this. For example, we take one example, paste it here. Okay, this is how it look like. Okay, so you observe here. So this is called SM block. Okay, so this block consisting of okay, only one state. Okay, only one state it has got. Okay, but here is one condition is there, another condition is and two conditions we observe that. Okay, so suppose three conditions that we have seen, and the output also we can observe that two output conditional outputs also there, but only one state is there. So if any SM state is having this kind of property, this is called SM block, right? So, and one more thing is that you should note that it consisting of only one entrance. Note, we'll write one note here. Note. It has only one entry, but can have more exit paths. More exit paths, right? That's what we understand about this. Okay. Now let us take another important definition about this one. Equivalent SM blocks. Next one is, I hope you understand this SM block, right? Equivalent SM blocks. Okay, so if two blocks can we can say that equivalent, because that means there is the SM block is not unique. Okay, so SM block can be modified in order to perform the same operation. Okay, so therefore there is no unique SM chart for a particular application. Okay, that application can be understood by different ways of SM blocks. Okay, so many methods are there. So for that one, so for the sake of definition, I'm writing on top. The SM chart is not unique. SM chart is not unique. Okay, it's not unique. So therefore, let us consider one example. If you consider this one, see here, so the A and B are equivalent to each other. Okay, the same function it is performing. Okay, so but here, so what is happening here? After x is equal to validated, then x2 will be evaluated. The same thing can be equivalent to say that first x2 will be evaluated first, and then we have to evaluate the x1. Okay, so this is also not that much clear, so I will take another example. So for example, you take one example. For example, y is equal to a plus bc. Okay, for example, y is equal to a plus bc. So I want to draw the state diagram for this one. Okay, what is the best possible way that we can do? Let us look at here. For example, see here, consider the first diagram. Okay, consider the first diagram. What is happening here? So now, actually, what we want to say that y is equal to 1. For example, if you draw the truth table for the this one, for example, a, b, c, and if you write y, okay, so y will becomes 1 for particular combinations, y is equal to 0 for particular combinations. Okay, so that means y is equal to 1 means that the output is equal to 1. If y is equal to 0 means the output is equal to 0. So no need to say that 2 times the output value. If you say that the output is equal to logic 1, if you're not mentioning that one, the output is equal to 0 only. Okay, fine. So for example, if you have a state diagram, for example, a digital system, something like this, its responsibility is that it produces a Y signal based on A, B, C. Okay, I want to define this digital system with the help of state diagram, state chart, SM chart. Okay, so therefore, for example, the state of the system is S0. If you want to check this evaluation, so this is equal to 1 if this expression is true. Therefore, it will produce the output is equal to 1 and go back to the initial stage. Okay. For example, this is expression is false. Then again, but it won't produce the output signal as logic 1. It produces the logic 0 output and again go back to the initial stage. This is the one way. So it is equivalent to say in a different manner. Okay. So something like this. For example, A plus BC that we have written. So when this becomes logic 1, if A is equal to 1, undoubtedly no need to verify for the BC, the output is equal to 1. Am I right? That's what we are doing here. We need to check S is equal to 1. Whether S is equal to true, then it will produce the logic 1 by Z is equal conditional output and go back to the, sorry, so something like this. It will go. The output is going this way and go back to the initial stage. Okay, that is the one method. Now another way is that, so for example, A is equal to 0. Then obviously we need to check for the BC. certainly B must be 1 అయి ఉండాలి, C must be 1 అయి ఉండాలి. Then only the output is equal to 1. Right? Is it clear? So in that situation, if BA is equal to 0, for example, then we need to check for C and we need to check for B. B must be A, C must be 1, B also must be 1. Then only the output is equal to logic 1. And again, once it is completed, it will go back and to the initial stage. Okay. So if C is equal to 0 అయినప్పటికీ, B is equal to 0 అయినప్పటికీ, output cannot be Z1. It is directly, it will go something like this, it will go directly to the output value, right? So therefore, from this example, we can understand that the SM chart is not unique. Okay, so therefore we can manage the SM chart in different way in order to fulfill the same operation. Okay, so that is what the conclusion about this equivalency in SM charts, right? So another one point is that whenever we are drawing the SM charts, we have to keep in feedback paths. So care must be taken on feedbacks on SM charts. Okay, so something like this we should not write. Okay, for example, I consider copy. I should paste it here. So these type of feedback paths are not allowed. So far we have seen that. So far we have seen that if you see previously also, this feedback path is going in this way. Okay, not directly to this one, in this one. So the feedback paths are going in this one and go to the previous. But once it is completed, you should not give the feedback in this way. There is no meaning in that sense, in that feedback notation. Okay, so when you are writing the feedbacks, care must be taken. Okay. Okay, fine. Okay, so another 2 minutes are there. I'll consider another point also. SM chart forms equivalency. Better you write it as equivalency in SM charts forms. So there is a serial form is there, parallel form is there. It is possible to convert the serial SM chart into parallel SM chart, vice versa. Okay, so just only thing is that for readability purpose as well as for simply understanding the operation, we use these methods. Okay, not necessary to write it is not necessary to convert the serial to parallel to serial. Okay, which one is better way to understand, use that one. But there is an options are there. It is possible to convert from one form to another form. Okay, so just for diagrammatically I want to show that what is the meaning of that one. Copy and paste here. Okay, so normally this is treated as a serial and parallel form. Okay, so you can observe carefully. This diagram is a self-explanatory. You can observe that only one state is there. Okay, only one state, but different forms are connected in parallel. Okay, things are connected in parallel. So but it should have only one particular exit. Okay, one entrance and one exit. One exit. Okay, so whereas here also the same way, but serially it is connected. Once this is completed, so and again we need to check here in this way, all these blocks are connected serially. The output of the first one is succeeded, then only we'll go to the second one. If second one is succeeded, then only we'll go to the third one. Okay, but here in this way, parallelly all these blocks are executed. Okay, so these importance of these particular notations we will see while taking the examples. For the time being, this is the theoretical part about the SM charts. Okay, so these fundamentals you should know when you are drawing the state diagrams. Okay, we will, in the next class we will we will see the how do we convert the state diagram into a SM chart. And for example, if you take any digital system, how do we generate the state chart or SM chart from the for that particular digital system? Okay, so thank you very much. We'll see you in the next class.